Good morning, class. We are looking at the final exam review covering from section 2.1 to 6.1. Here's the first part that we are going to cover. So as you can see, we have a lot of differentiation formulas. I hope everybody remembers all of them. You should be very comfortable with differentiation formulas. That's the nature of this course, differentiation and integration. It gets you ready for the next course. Delta y, by definition, is precisely f of x plus delta x minus f of x, whereas dy is f prime of x dx. The distance along the y-axis when it comes to the curve is delta y, along the tangent line is dy. They are not the same, but we can approximate it. Can approximate the delta y by dy. And the linearization simply means find the equation of a tangent line. That's all. Y minus y1 equals m times x minus x of 1. You don't have to memorize this formula. Understand that you have a pair, a comma f of a, and then find the derivative, f prime of x, evaluated at a becomes the slope, or f prime of a. And these are the definition of the limits. As far as e is concerned, we remember e is the limit of 1 plus 1 over n to the power of n as n approaches infinity, as well as the limit of e to the power of h minus 1 over h as h approaches 0 is equal to 1. Logs. If we understand this arrow, meaning b to the power of y is x, needless to say b is positive, b can't be 1, then all of these properties make perfect sense. For example, log 1 with base b, meaning any base is 0. If you look at this arrow, b to the power of 0 is 1. And the rest of it. And needless to say, numbers 3 and 4 refer to the fact that logarithmic functions, exponential functions, are inverse functions. So in the case of a common log, when we don't write the base, we write y equals log x, the base is 10. That's called the common log, and we can translate this into a common log, which is a specific case of a general case. In the case of a natural log, the base is e, in which case we call it y equals ln x. And again, we see the same properties. Exponential functions and logarithmic functions are inverse functions. Therefore, they are symmetric with respect to the line y equals x. And here's the change of base formula. The derivative of ln x, just flip it over 1 over x. The derivative of g of x, again, you flip it over by the chain rule times g prime. If the base is something other than e, then you also tag along 1 over ln b because of the change of base formula. And then the reverse process of differentiation would be integration. So, for example, the integral of k dx gives you kx plus c. So knowing that the derivative of tangent is secant squared, so the integral of secant squared x dx is tan x, just as an example. And then we have FTC, short for fundamental theorem of calculus, which says the derivative of the integration gives you the function back at the upper limit. And if capital F prime represents the derivative f of x, then the integral of a to b lowercase f of x dx is f of b minus f of a. This is a definite integral. This is a number. And the substitution rule, basically, you let g of x be u, and g prime of x times dx is du. I can't emphasize this enough. When you do substitution, the very first thing you have to write down, here's the u, here's du, and the integral of f of u du is called the substitution method, everybody. Let's get started with the first example. Given the graph of a function, state the values. Here's the function, and we are really interested in finding the limit of g of x as x approaches 2. And therefore, we're going to look at one-sided limit, the limit from the left and right. As you recall, one-sided limit says a function has a limit at a if the limit of f of x as x approaches a from the left equals L. Also, the limit of f of x as x approaches a from the right is L. Therefore, the limit exists and it's equal to L. As we approach from the left of 2. We are coming to this point, which has a y-coordinate 3. From the right side, we are approaching this point, which has a different y-coordinate, namely 1. Are they the same? No, therefore the limit does not exist. DNE short for does not exist. We are interested in finding the limit of g of x as x approaches 5, and again we look at one-sided limits. Notice as we approach 5 from the left and from the right, in both cases, we are moving towards this hole, and this hole has a y-coordinate 2, therefore the limit exists and it's equal to 2. Now, let's assume this point has a y-coordinate 1.4, which makes g of 5 1.4, which is not equal to 2. Needless to say, the function is discontinuous at 2 as well as number 5. However, here's the definition of a continuity. The limit of f of x as x approaches a equals f of a. Then it makes it continuous at a. And g of x can be continuous at x equals 5 if we redefine it, g of 5 to be 2, because it is simply a hole. This is called removable discontinuity. So this is removable. However, when we look at g of 2, besides the fact that it's not defined, there is no way to fix this discontinuity because there is a jump. This we can fix it, this we cannot. We want to find the limit of r of x as x approaches 2, 5, negative 3 from the left, negative 3 from the right. I'm reminding everybody as far as definition of a VA, short for vertical asymptote, is concerned. If the limit of f of x as x approaches a, or a from the left or a from the right, is either negative or positive infinity, then it gives rise to the equation of x equals a being a vertical asymptote. So as x approaches 2, from the left and from the right, both of them go down to negative infinity. However, 5, they blow up to positive infinity. Negative 3 depends. From the left of it goes to negative infinity, but from the right of it goes to positive infinity. And therefore, by the definition, x equals 2, x equals 5, x equals negative 3. Both of them refer to the same thing. X equals negative 3. Those are the vertical asymptotes, everybody. X equals negative 3, x equals 2, x equals 5, vertical asymptotes. Now, how do we find limits? One easy way, just plug in and observe. So what happens? The limit of f of x as x approaches a is a number, you're done. It's 0 over a number. It's equal to 0 and you're done. It's a number over 0. Remember, a number over 0, they used to say undefined, but ultimately it blows up to infinity or negative infinity. And you have to figure this out because 0 is the only number that the right side of it is positive, the left side of it is negative. We also have an indeterminate form. That's what we come across mostly in calculus: 0 over 0, infinity over infinity, infinity minus infinity, and so on. The limit of 2x squared plus 8x over x squared minus 16 as x approaches infinity. Whenever you have a fractional format, of course, it's a rational function, but in general, a fractional format, When x is approaching infinity, the technique is to divide by highest degree term in the denominator. In this case, is x squared, and simplify. As you can see, since x goes to infinity, this guy goes to 0, this guy goes to 0, you get 2 over 1, and that's the final answer. However, it's really nice to simplify it first. It makes it a tad easier. Notice we can factor the x plus 4 out, and the expression becomes 2x over x minus 4. If we had that one, then we would have to define, because again, x is approaching 8, we have to divide by x this time. But needless to say, you receive the same answer, namely 2. What about this one? If you plug in -4, you will end up with 0 over 0 class. And the technique is factoring. So we look at the factored form. And now if you plug in -4, you get -8 over -8, which is positive. In this case, if you plug in 0 just the way it is, it will give you the answer, which is 0 over -16, which is 0. If you put it into its factored form, also it gives you 0 over -4, and both of them are 0. So it doesn't make that much of a difference in this case. However, working with a factored form is easier. What happens when x approaches 4 from the left or 4 from the right? First and foremost, please understand, if you plug in 4, the numerator is 64 in both cases. The denominator in both cases is 0. Okay. And 0 is the one that creates a problem in the denominator. First of all, let's look at the factored form. Okay. It's easier to deal with the factored form, everybody. So we want to look at the factored form. Now, if I plug in 4, everybody, in both cases, I get 8 over 0. However, it is 4 from the left. When you plug in, please understand, in the case of a numerator, 2 times 4 from the left, that means like 2 times 3.9999 is almost 8. The numerator is 8 or close to that. But the denominator is 0. 4 from the left, you pick up a number such as 3.9, and you say minus 4 makes a negative 0.1. So it makes 0 from the left, which makes it positive over negative is negative, negative infinity. However, in this case, if I plug in 4, then I get 4 from the right, like 4.1 minus 4 is positive 0.1, which makes this one 0 from the right. Positive over positive makes it positive, therefore the answer is positive infinity. So you want to be able to distinguish between the two and see the methodology by which you can easily come up with the answer. We want to find the limit, and if you plug in, you basically get 12 over 4 or 3. I'm reminding you of the following. Negative exponential rule, e to the power of negative 1m is 1 over e to the power of m. So e to the power minus t is 1 over e to the power of t. And because t is approaching infinity, this denominator becomes infinity, goes to infinity, and this is 0. As t goes to infinity, I hope you recognize e to the power of t goes to infinity, the denominator goes to infinity, and the answer is 0. If you look at part C, because the denominator is 4 plus 3 e to the power of t, and t is approaching negative infinity, becomes identical to part A. And we get 3. And in this case, if t goes to 0, that means this becomes 1. So 12 over 4 plus 3 e to the power of 0. This is 1. 3 and 4 is 7. 12 over 7. To differentiate this, we bring the bottom up. So f prime is 12 times negative 1 times the same thing to the power of negative 1 minus 1 or negative 2. We are looking at extended power rule. And by the chain rule times the derivative of the inside, which is 3 to the power of t. When we put this together, 12 and negative 1 minus 12 and 3, negative 36 e to the power of t. This goes down, becomes positive as far as the exponent is concerned. Let's find the limits, and because in this case x is approaching infinity, and if you plug in, you get infinity over infinity class. So if you plug in, you end up with infinity over infinity here. You plug in, you get 0 over 0 here. You plug in, you get 0 over 0 here. So because x is approaching infinity, we are going to use the same technique with rational functions. That means divide by highest value. The highest value in the denominator is e to the power of 3x. So when you divide everything by e to the power of 3x, what happens? This one divided by this is 1. This one, I hope you divide by this, you get e to the power minus 6x. This is again 1, and this one, e to the power minus 6x. Because x is approaching infinity, these two go to 0, so the answer is 1 over 1, or simply 1. This gives you 0 over 0. You're dealing with a complex fraction. So you're dealing with a complex fraction. So the technique is LCD, which is simply 4x. Multiply and divide by. When you do so, this times the numerator results in x plus 4. The denominator, just keep it as a product. X plus 4 cancels out. You get 1 over 4x. Plug in negative 4, you get negative 1 over 16 as the final answer. In part C, if you plug in, you get 0 over 0. Since you have a square root, the technique is conjugate. So what was the conjugate? The conjugate of A minus B is A plus B. Their product is A squared minus B squared. So you multiply by the numerator with the plus 1 instead of minus, and you divide by it. The denominator doesn't change. You write it as a product just the way it is. And now this is A minus B, A plus B, which means A squared. That means this comes out minus 1 squared, which is 1. These two cancel each other. H cancels out the H and becomes 1 in the numerator. If you plug in 0, you get square root of 1, which is 1. 1 and 1 is 2. So you end up with 1/2 as the final answer. So it's important to understand infinity over infinity can give you anything. It gave us 1 here. 0 over 0 can give us any number, or in some instances it blows up to infinity. This one, the same thing. You have to work it out. G of x is defined as 1/2 x plus 3 for x less than -2 and x minus 1 for x larger than or equal to -2 is G of x continuous at x equals -2, why not? First and foremost, why are we looking at x equals -2? This function, you can think of it as y equals 1/2 x plus 3, and this function, you can think of it as y equals x minus 1. Each one is a linear function, which means from negative to positive infinity, they are and that's their domain, and they are continuous, both pieces. So the only one that you have to check is the endpoint. The way it works, we have to look at three things. We have to look at the functional value, and we have to look at the limit meaning both sides. So the functional value means the function evaluated at -2. So it uses the one that has the equality. So it uses this part, and we're going to write g of -2 notation x minus 1 such that x equals -2. If you plug in, you get -3. So the function has a value of -3 when x is -2. What about the left-sided limit? You use the piece that says less than. So you are going to plug it into this piece. -2 divided by 2 is -1 and 3. They add up to 2. We're going to look at the right side. And for the right side, you look at the one which has a greater than. So we're going to look at this piece. And again, we get -3. As you can see, the left and right have different limits. The limit does not exist. So the limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, the limit of g of x as x approaches -2 does not exist, and therefore g is not continuous at x equals -2. Just notice that g of x is continuous at x equals -2 from the right. Why is that? If you look at the functional value, and the right-sided limit, they are equal. So the terminology is this: g of x is continuous at x equals -2 from the right. However, it remains that the g is not continuous at x equals -2. That's important not to mix them up. We want to find the limit of cosecant x sine of sine x as x approaches 0. Just cosecant x is 1 over sine x. So we are going to write this expression divided by sine x. And I'm going to remind everybody, by the way, now that we have L'Hopital's rule, we can use L'Hopital's rule, okay? Because when x approaches 0, this is 0, this is 0, sine of 0. So you get 0 over 0, you can use L'Hopital's rule. However, what we learned in the beginning, limit of sine theta over theta as theta approaches 0 equals 1. Limit of cosine theta minus 1 over theta as theta approaches 0 is 0. And notice, if you think of this as theta, because x approaches 0, so does theta. And that's important to understand. X approaches 0, theta approaches 0. Okay, notice we have changed that. And according to that, the answer must be 1. And that's extremely important to understand, okay, class, how we arrive at it. Questions? All right. If we plug in, we get 0 over 0. Again, you can use L'Hopital's rule now, but going back to the methodology we learned before, if they were identical, we could go with that method. So we can multiply this by x, and we can multiply the numerator by x. The result is, if I multiply both of them by x, the result is this becomes x squared, which is identical to that. And so I'm looking at limit of x as x approaches 0 and limit of this part. So this numerator, limit of x as x approaches 0, and then this times this is x squared. So now this part, everybody, think about this as theta. And remember, x squared or theta, they go to 0. And so what is the answer? We know x approaching 0. So this is 0. We know this is 1. The product of 0 and 1 is 0. Or, as I said, you can use L'Hopital's rule at this point. G of x is sandwiched between 2x and x to the power of 4 minus x squared plus 2. For all x, evaluate the limit of g of x as x approaches 1. So we are going to find the limit of the left side and the right side as x approaches whatever this one says, which is 1. Clearly, this is 2 times 1 or 2. We do the same thing to the right side of this inequality. And if we plug in 1, we get 1 to the power of 4 minus 1 squared. They cancel each other, plus 2, and the answer is 2. Now, according to the squeeze theorem, where it says if f of x is less than or equal to g of x, less than or equal to h of x, when x is near a, except possibly at a. So it doesn't matter what happens at a. And limit of f of x as x approaches a equals limit of h of x as x approaches a equals L. So the left side and the right side, they both have the same limit. Therefore, the limit of the one in between, the function in between g of x as x approaches a equals L, this is called the squeeze theorem. So by the squeeze theorem, the limit of g of x as x approaches 1 is 2 by the squeeze theorem. You must mention by the squeeze theorem. Prove that the limit as x approaches 0 from the right of square root of x times the brackets 1 plus sine squared 2 pi over x equal to 0. This you have to use a trick, if you will. We know that sine is always between negative 1 and 1. Now we are going to make this expression somewhere using this one. So the fact that sine is between negative 1 and 1, it makes any sign between negative 1 and 1, including sine of 2 pi over x. Now, we're going to square both sides, and I want you to pay attention to. If a number is between any negative and any positive, and you're squaring it, the positive gets squared up. But the negative, it's negative 1, negative 2, negative 0.4582, it makes no difference. When you square it, this really, you can't square it. You have to change it to 0. So again, I want to make sure everybody understands that one more time. When you square all sides, this is clear, this is clear. What happens to negative? Negative basically goes away. So it can be between 0 and 1. We want to make it look like this. So what do we need to do? We have this one. Let's add 1 to all sides. So we have the brackets, everybody. We want it to look like this. Square root of x is missing. Let's multiply by square root of x. So if I multiply every side by square root of x, I get this one. And by the way, can I do that? Remember with the inequality, if you multiply by a negative number, it flips over, but x is approaching 0 from the right, which makes square root of x a positive value always, and therefore the sign doesn't change. And if you look at this part, is exactly what we were looking for. Now we take a limit of the left and the right as x approaches 0 from the right, and as you know, clearly it becomes 0. And therefore, this becomes 0 by the squeeze theorem. So the limit as x approaches 0 from the right of square root of x, brackets 1 plus sine squared 2 pi over x equal to 0 by the squeeze theorem. We want to find the limits, and we're dealing with the square root, and x is approaching negative infinity. So I want to show you the technique that I'm going to use here. Over here, I noticed that I have x to the power of 6 and x to the power of 6. If you take a root, it's the same as x cubed. Of course, you have to pay attention to the sign, and I'm going to explain that in a moment. So if I take x to the power of 6 out, what happens? In case of a limit as x approaches infinity, means x is larger than 0. As you know, square root of x squared is the absolute value of x, or x. And in case x approaches negative infinity, for x less than 0, square root of x squared is still absolute value of x. However, this becomes negative x. Please understand the meaning of minus x is the opposite of x doesn't mean a negative value. Okay. And with that being the case, if you have x cubed is the same as x to the power of 6, x to the power of 6 under the radical when x is positive, but it becomes negative of that if x is negative. So you have to factor x to the power of 6, and you do that when you take this out, becomes negative. Why? Because of this negative infinity. Let's divide the top and the bottom by x cubed, or just multiplied by 1 over x cubed. So this goes away. This becomes 2 over x cubed. This becomes minus 1. And since x is approaching negative infinity, 1 over x to the power of 6 goes to 0. 2 over x cubed goes to 0. Okay, so this goes to 0. This goes to 0. This is 4. Square root of 4 is 2. Negative makes it negative 2. Over negative 1 is positive 2. So I just wanted you to be exposed to that and be careful when x is approaching negative infinity. In short, if it's approaching positive infinity, you have nothing to worry about. If it's negative infinity, it depends. By the way, just for the sake of argument, if it was square root of x to the power of, let's say, 8, would be x to the power of 4 out, and both of them will be the same. Because even exponent makes the negative positive as well when you raise it to the power. All right. We are going to differentiate, and we are going to use the quotient rule. And if I'm differentiating this, I'm going to write f over g, and I'm going to write the formula for me, and I'm going to follow that. And the reason I mention it, because a lot of students, they use ddx of this, ddx of that, and it becomes way too long. So f prime, the top gives you just cosine, times the bottom, f prime g. I need the g, just put it in x plus cosine, minus g prime. The derivative of the bottom is 1 minus sine x times f 1 plus sine x, and then over g squared. Just write the bottom and square it in a parenthesis. You don't have to do anything. Practically, we're done. As far as the differentiation is concerned, all we have to do is simplify. And this is a minus b, a plus b. Okay, and we get a squared minus b squared. So I've shown you that. So a minus b, a plus b, a squared minus b squared. Remember Pythagorean identities, everybody? Sine squared plus cosine squared is 1. When you know that, you should know that 1 minus sine squared is cosine squared, 1 minus cosine squared is sine squared, and so forth. We also have tan squared plus 1 equals secant squared, 1 plus cotangent squared equals cosecant squared. So those are some identities from trigonometry. So we're going to replace this with cosine squared. Therefore, these two go away, and we are done. X cosine x remains in the numerator, and the denominator is x plus cosine x quantity squared. We don't have to make any changes. We keep it intact, and we are done. We want to differentiate those, and I'm going to remind you the derivative of e to the power of x is itself. The derivative of e to the power of kx is itself times k by the chain rule. The derivative of e to the power of g of x is itself times g prime by the chain rule. So let's see what happens here. So the answer is itself. By the chain rule, I need number 5. This one, the answer is itself. By the chain rule, I need the derivative of tangent, which we should know is secant squared. And we are done. Now, this one, I want to make sure that we know what's going on. So I'm going to rewrite this as e to the power of 2/3 x. So the answer is itself times the derivative of the exponent is 2/3. And now we're done. What happens when the base is no longer e? Again, the answer is itself. If the base is not e, times natural log of the base, ln b. If it's b to the power of g of x, again, itself, ln b, that's really by the change of base formula, and then g prime by the chain rule. So the answer is 3 to the power of x. And then because the base is not e times ln 3, and we just rewrite it so it becomes clear that it's 3 to the power of x times ln 3, we are done. Y equals 2 to the power of 7x, the answer is itself. Any exponential, the answer is itself. Is the base e? No. Times ln 2. Is the exponent x? No. It's a function of x times its derivative by the chain rule times 7. And we just rewrite it. The reason we put this in a parenthesis because if we don't, one may think it's 7 ln of 22 to the power of 7x. So be careful the way you write things. To differentiate this, we're going to bring this up to the power of -1/2. This is elementary algebra. We're going to use the extended power rule. 4 remains times -1/2. And then the same thing to the power of -1/2 minus 1. And by the chain rule, the derivative of the inside, which is 2x. 4 and -1/2, -2, and 2 is a 4x with a negative sign. So -4x, the same thing to the power of -3/2. And this goes down, becomes +3/2, or becomes a square root. So -4x square root of x squared plus 3 quantity cubed. F of x is 3x times 3 to the power of x. You can think of this as y, if you will, and this is f times g, and you're using the product rule. Okay, everybody? F prime g plus g prime f. So the derivative of the first piece is 3 times the second piece. This is f prime g plus g prime f. The derivative of the second piece is an exponential is itself times the base ln 3 and times the 3x, which is the product rule f. So let's write at top of it. We have, let's see what color I want to use. Okay, so this is f prime g plus g prime f. And notice the exponent here is 1. The exponent here is 1. So I can write this as 3 to the power of 1, 3 to the power of x. That means 3 to the power of x plus 1. 3 to the power of x and 3, the same thing. 3 to the power of x plus 1, ln 3 and x remain. So this is 3x to 3 to the power of x plus 1, and this is 3 to the power of x plus 1. ln 3 remains, x remains. Please understand this one and this one. So if I factor the 3 to the power of x plus 1 out, this gives me 1, and this gives me whatever is left here. ln 3 times x, we write it as x ln 3 because if you put the x here without the raised dot, one may think it's ln of 3x. That's why it's better to write it in this format. We want to differentiate this. We are going to use the chain rule. However, before we do that, anytime you have a fraction, ask yourself, can I simplify it? And the answer is yes, because I can make up two fractions. This gives me x, this gives me 4. And that is a simple case now. 6 times x plus 4 to the power of 5 times 1, because the derivative of the inside is 1. I don't write it, and I'm done. It's that simple. So sometimes, we can take the easy way out. But over here, there is no way to simplify it. I have to go with the extended power rule. So 5 times the same thing to the power of 4. And now times the derivative of the inside, which requires the quotient rule. And so this is the f function. This is the g function. If you f prime g, so f prime is 2 times x minus 8 minus g prime. The derivative of the bottom is 1 times 2x plus 3, and the bottom squared. And now you're done with calculus. We are going to simplify this last fraction. The numerator is 2x minus 16 minus 2x minus 3. And these two cancel each other. These two add up to negative 90. Okay. So it's clear that this one and this one are at the bottom, this one and this one and this one are at the top. However, one may not recognize this one as 2x plus 3 to the power 4 over x minus 8 to the power 4. That's why I'm going to write it in this format. And here's the last fraction. So what's it in the numerator? 5 times negative 19, which makes it negative 95, and this guy to the power of 4. What's in the denominator? X minus 8 to the power of 4 plus 2. And that's the final answer. Again, you don't have to necessarily take this step. You can go from here to here as long as you understand what you're doing. I just wanted to be clear. We are differentiating implicitly. I'm going to put a raised dot here. So we recognize this as f times g. And therefore, we are going to use the product rule. So 4x squared gives me 8x times y plus y gives me y prime or dy dx times 4x squared. So y prime times, by the way, y prime makes it a tad easier to use, but you got to be careful with your independent variable. The advantage of dy dx is that it is telling you what is the independent variable. In this case, we get 4y y prime, and any number results in 0. We are done with calculus. We are going to use algebra to fix this, meaning we're going to put these two together, and we're going to move this one to the right, which becomes negative. And these two, you can take the 4y prime out. And now you divide by 4 times x squared plus y. And when you do that, you simplify it to negative 2xy over x squared plus. We're going to differentiate this, and I hope you remember the fastest and easiest way is to just say cosine and pause. Never mind the rest of it. The answer is negative sign. But every sinusoidal function requires an argument, so you have to use the same argument. The chain rule says multiply by its derivative, 12t cubed, and that sits in front, and you're done. Differentiate y is tan to the power of 10 of sine x cubed. You can even, if it helps you, you can just get rid of this and make it like g of x and tan to the power of 10. It's important to understand this means the following. Tan of sine x cubed to the power of 10. The reason I want to write this because I want you to see that you are using the extended power. So 10 sits in front. Same thing to the power of 9. So when you want to write the same thing to the power of 9, you have two choices. You can put it in brackets to the power of 9, or say 10 to the tan to the power of 9 sine x cubed. Now, this is g of x. Remember, this is g of x, everybody. This is g of x. So now you need to differentiate this by the chain rule. So 10, the same thing to the power of 9, and now differentiate it, put it here. Tan of g. So what is the tan of g? The derivative is secant squared of g. Secant squared of sine of x cubed. By the chain rule, you need the derivative of sine of x cubed. What is the derivative of sine of x cubed? Cosine of x cubed. And what is the derivative of x cubed? 3x squared. So I want to make sure we understand that. So first, we need to differentiate this, which is this one. To differentiate this, tan gives you secant squared. Then you need to differentiate this, gives you cosine x cubed. Then you need to differentiate this, gives you 3x squared. There are several layers. If it makes it easier, everybody, write this as tan of g of x to the power of 10, and then differentiate 10, tan to the power of 9, then it becomes 10 tan of g of x to the power of 9 times g prime of x. And now you have to times secant squared of times, I thought I put the secant squared, I didn't. Times secant squared of g of x times g prime. So if it makes it easier, you can do that. Anyways, you're done. You are going to rewrite it in the following manner. 10 and 3 gives you 30. We put the x squared in front, cosine of x cubed, tan to the power of 9 of sine of x cubed, and secant squared of sine of x cubed. Basically, you can put those in the order you want, but it's a good practice. Minimum, this has to be in front.